start from the first part, the basic introduction of theory of computation. So our subject is theory of computation. So we should understand what theory of computation is. So going on by the definition provided here, it is the branch of computer science and mathematics that focuses on understanding the fundamental limits and capabilities of computing devices. So we all know that our devices have the computational power to perform various operations. So, but then what is the primary foundation for all this to happen? So the primary foundation is what arises from theory of computation. So this subject or this branch of computer science is pretty old, and it has a great importance when it comes to the gate exams or the interviews or even our university exams for that matter. So looking at the other definition, it explains us how efficiently problems can be solved on a model of computation using different algorithms. And along with that, we also check if the problems are solvable or not. So when we further look into the types of the key areas of theory of computation, we come across the problems which can be solved or the problems which cannot be solved. It is called as computational theory. Okay. So speaking of the key areas of study in theory of computation. So the first one we have is automata theory. Automata theory comprises of finite automata, push-down automata, Turing machines. Here we have the regular languages and context-free languages. All these come under automata theory. Then again, as I said, formal languages is again one more topic. In that we have grammars and formal languages, type 0, type 1, type 2, type 3 grammars. Next we have is the computational theory, which I told. So in this, we'll check if the problems are like it is decidable or undecidable. And along with that, we also have the complexity theory, that is to check if the problem is NP type or NP complete or NP hard. So we'll be understanding all this in the further upcoming videos. So stay tuned and like, share and subscribe to my channel so that you get all the updates related to theory of computation subject. So moving on further, now we'll look into the main part, okay, from exam perspective or from the interview perspective or from gate perspective, we'll study the topics now. So the first one we have here is automata theory. So automata theory is study of abstract models of computation. So what does automata mean? Automata is like, automata is the it derives from automation. Okay, so it is, automation is finite representation of a formal language. So you might say, what is a formal language? Formal language is a set of languages which are defined by making use of the grammars and the regular expressions. We'll understand this further, but as of now, the definition of automata theory is, automata is finite set of representation of formal language that may be an infinite set. So any computation or any sequence of execution of automata So any sequence of execution is mainly derived from or is essentially from a string manipulation system. So this is like, string manipulation has a great importance when it comes to understanding the automata theory. Now we'll look into the applications where and all automata theory is used. So the first one is in compiler design. So when you come across the lexical analysis in compilers, we make use of automata theory. Then we have the text editors. Then along with that, we have the switching theory. In switching theory also it is used. Then we have, in order to design the circuits, we make use of automata theory. Then in order to understand the networks also, we come across the concepts of automata theory. Along with that, if we have to study the communication protocols, we'll be using these concepts. Now moving on further, this was about the intro part of automata theory. Now we'll look into the central concepts of automata theory. What are the central concepts? These concepts are like a foundation which will help us to understand the subject further. So the first definition which we come across is called as alphabet. So let us understand what alphabet is. Alphabet is a set of finite and non-empty set of symbols. So alphabet is usually depicted with the symbol called as sigma, right? The symbol is called as sigma. It is denoted by making use of sigma. So what does alphabet comprise of? Alphabet alphabet could be, I'll write all the possibilities. It could be 0 or 1, that is the binary numbers, or it could be the lowercase values, lowercase characters, or it could be any digits, or it can also be like operators or special symbols, plus, minus, or any operator or a special symbol, let's say id, or let me write anything. It could be anything for that matter. Okay, so all these things comprise of ASCII characters. So this is the definition of alphabet. Okay, moving on further, the next topic which we come across is string. String, or it is also called as word. Okay, so if you come across string or word, understand it is the same, strings or word. So explaining, string is a finite set of sequence from the symbols which are chosen from alphabet. It is finite set of symbols which are chosen from alphabets. So let us consider an alphabet. Let's say sigma is equal to 0 comma 1. So this is an alphabet which comprises of binary numbers. We have seen binary numbers here, right? So sigma is alphabet comprising of binary numbers. So from these symbols, we will derive a meaningful string or a word. Okay, so I can write or I can depict the word or string as W is equal to, if I write 1011, so this 1011 is a string, or it is a finite set of symbols which are derived from the alphabet which is mentioned above, right? So this is what a string or a word refers to. Next topic I have here is empty string. So what does an empty string mean? Empty string means a string with zero occurrence of any symbol. Although we have specified the alphabet, but we are not writing anything, right? In that case, it is called as empty string. Empty string is represented by epsilon symbol. Epsilon or lambda, both are same. Okay. In some textbooks you can find epsilon. Some places you can find lambda. Okay. Next we have is called something called as length. Length of string. So by definition, you can understand length means the number of positions for a symbol in the string. Okay. So or we can also tell it as like the length of string is the number of symbols that are used. That are number of symbols present in the string is called as the length of string. So let me take the same example which I specified here, 1011. So how many characters are there here? 4 characters are there, right? 1 0 1 2 3 4. So I can say that the length of this particular string is 4 units. Okay, moving on further. So this was about the length of string. Now again I have two more concepts under this. The first one is concatenation. Concatenation of strings. So let me take two strings w1 and w2. Okay, let me write it here. W1 and w2 be two strings. Okay, so let w1 be 0 1 1 0 and let w2 be 1 1 0. So if I write concatenation of w1 and w2, it will be 0 1 1 0 and 1 1 0. So I am combining those two. Okay, So, but can I say that W2, W1, if I concatenate, will it be the same? No, it won't be the same, because 110 will come in the first and 0110 will come in the next. So we can say that W1, W2 is not equal to W2, W1. So this is one condition. Second condition, if I take W1 as some digit, some string, I have taken some string in W1, and W2 is empty, okay, epsilon. Then I can write W1, W2 concatenation, I'll get 1, 0, and W2, W1 concatenation also I'll get 1, 0. So here I can say that W1 is equal to W2. So this was about the concatenation part. Let's move further. Moving on further, we have reversal, topic called as reversal of strings. So let's look into what reversal is. So reversal means we are writing whichever string we have obtained in reverse order. So it is depicted by W to the power R. So if I take W, let me write the definition here, writing in reverse order. Let me take W as 10011. The string is 1011. Reversal of the string could be written as 11001. Okay. There we have concept called as power of alphabet. Power of alphabet is like for any given alphabet, we know alphabet is represented in sigma. For any given alphabet, sigma, we can write power of alphabet as sigma to the power n. So sigma to the power n will depict set of all strings of length n over alphabet sigma. So I can write if sigma is equal to 0 comma 1. So the alphabet comprises of binary numbers, okay, binary digits, okay, 0 and 1. Then I can write sigma to the power 0, power of alphabet sigma to the power 0 could be epsilon, because this is a empty string or string with length 0. If I write sigma to the power 1, then I can represent it as 0 or 1. So either it could be 0 or it could be 1. So here length of the string is 1. Then if I write sigma to the power 2, it could be combination of two characters or two symbols. It is 0 0 or 0 1 1 0 1 1. So here if I again if I check, length is 2 for each and every character. Again if I write sigma to the power 3, then I can write 0 0 0 0 0 1 and so on till 1 1 1. So here again length is equal to 3. Now if I continue writing this till sigma to the power n, I can write it as sigma to the power n means I can write set of all strings of length n over sigma. So here one more thing to note, a very important topic I would say, is if I write sigma star, it is equal to sigma 0 union sigma 1 union sigma 2 union sigma 3 so on till sigma n. It is combination. This is called as clean closure, okay. This is one topic. Another topic which we have is positive closure. Positive closure means it will start from sigma 1 union sigma 2 union sigma 3 and so on till sigma n. So we can say that that positive closure is equal to clean closure minus epsilon. That is, here sigma 0 is not being included, right? So we can write it as, this is very important. So as I told, you can write it as sigma star minus epsilon. Okay, so this was about the power of an alphabet. Moving on further, again, next topic, very important topic which we have is called as languages. So languages means, languages is a set of strings of which are chosen from, uh, I'll write set of strings which are chosen from sigma star. Sigma star where sigma is particular language, or sorry, a particular alphabet here. So from this particular alphabet, if we are deriving several strings, it is called as language. Okay. So here we can say that uh, Language is a subset of sigma star, because in sigma star we define all the possible values, right? So language is a combination or a subset of it. Okay, so we can write that language is subset of sigma star. Language is depicted by L. Okay, next let me write one more point here, that is a language over sigma need not include strings of all symbols of sigma. That is, so once we have established that L is a language over sigma, so I can say that a language over sigma need not include strings of all symbols of sigma. So once we have established that L is a language over sigma, it is done, it is considered as one language. For example, let me write an example here. The language of all strings consisting of n zeros followed by n ones with an equal number of zeros and ones. Okay, so for that I can write language is equal to either it could be empty, or it could comprise of 1 0 and 1 1, or equal number of zeros and equal number of ones, and so on. Next, I can write a string for zeros, only zeros. Okay, then I can write either it could be empty or 1 0, 2 zeros, 3 zeros, and so on. Or I can write it for like it could be anything. Okay, so if I write this was equal number of zeros and ones, so this was for increasing order of zeros. If I write for example, if I consider the lowercase values, I can write equal number of a's and b's. So for that it will be epsilon empty 1a 1b, sorry, ab would be there, ab would be there, that is 1a 1b, or it could be 2a's and 2b's, or it could be 3a's and 3b's, and so on. So here equal number of a's and equal number of b's are present in the language. So this is an example of infinite language. It can continue. Okay, there is no end to this, right? So one more thing I can say that what is, now that we have come to language, we'll also understand what are the various operations that we could perform over the languages. Okay, so first one is the union operation. So let us consider two languages, L1 and L2 be two languages. Okay, so I can say that L1 union L2. Let me take L1 as 0 1 1 0 1. Let me take L2 as 1 1 0 and 0 1 here. So combination of these two or union of these two, I would get 0 1 1 0 1. That is, first whatever was there in L1 is placed here. Along with that, L2 is also placed here. That is, I have 1 1 0 and 0 1 here. So this was about the union. Next, intersection. Intersection, if I write L1 intersection L2, I would get, if I intersect these two, what would I get as remaining here? So I'll get 0 and 1 as remaining here, right? Next, I have complement. So complement, I can depict as L1 dash, right? Or L1 to the power above, I'll draw a line. So this is equal to L1, I had 0 1, so it will be 1 0, and here 1 0 1, so here it will be 0 1 0, and yeah, this is the complement of the language. Then I have reversal. Reversal, as we have discussed, reversal of strings, on the above to the power we'll write r here. So L1 reversal, L1 reversal, we have 1 0, and here we have 1 0 1 again. If you reverse 1 0 1 from this way or this way, it is the same, right? Next we have is concatenation. Concatenation is L1 L2, right? So here it would be, I will be concatenating strings of L1 followed by the language L2. Like each and every string needs to be considered here. So here it will be 0 1, and along with that 1 1 0 0 1 and 1 1 0 0 1 and 0 1, 1 0 1 and 1 1 0 and 1 0 1 and 0 1. Let me write it here, 0 1 and 1 1 0, followed by that 0 1 and 0 1 and 1, and next I have 0 1 0 1 Next I have 10 1 1 1 1 0. Next I have 10 1 1. Next I have 1 0 1 0 1. I have written those elements as it is, and along with that I have also combined or concatenated it here. So this was about the languages part. Okay, so now that we are done with all the basic concepts, now we'll look into what finite automata is. Finite automata is a very important topic, so either they can ask the definition, or there could be definition would be asked. Yes, finite automata is a mathematical model which is used to study what an abstract machine or abstract computation does. So mathematical model used to study the abstract machine. Now tell me, what is an abstract machine? Abstract machine or abstract computational device is a machine which has majorly three components. Those three components are: firstly, there has to be an input, there has to be a control unit, and next there has to be a output. What input, in terms, it has to be either symbols or alphabets. Control units are the states, and output is either it is rejected or accepted. We'll understand what control units are, what is rejection and acceptation further. Okay, so we can say that finite automata is also known as finite state machine. So depending on a certain input, a certain output should be generated. That is what finite state machine speaks of. So input is processed by various states. So once you give the input, it is processed in the control unit, right? Depending on various states. So the start state is when the start state is the initial state, and along with that we have the final state, that is the accepting state. Between the start state and final state, there will be different what I say, transitions happening. Okay, so let's understand these representation of finite state machine. Okay, so let's see the representations one by one. If I draw a circle, it is one state. Okay, what is a state? State is an intermediate situation between the input and output. So at state there could be different operations happening or transitions happening. Okay, next, if I have a circle and an arrow, then it is called as start state, or it is called as initial state. Then if I have just an arrow, then it is called as transition. What is a transition? Transition is upon a particular input, we move from one state to another state. So this movement from one state to another state is called as transition. Okay. Next, if I have double a state which is double circled, it is called as final or accepting state. So this was about all the basic representation which we make use in terms of the finite automata, right? Next, moving on further, we have representations of automata. Okay, so this was about finite automata. Now let's see how automata is represented. So in order to represent automata, we'll be making use of three main things. Okay, so the first one is transition diagram. The second one is transition table. Next we have is the transition function. And we also have the structural representation. We'll look into that further. So what is transition diagram? Transition diagram is a graphical representation. Transition diagram is a graphical representation of the finite automata. It is also called as like a transition diagram starts with the initial state, and there could be multiple states in the middle, followed by a final state. So let me draw an example transition diagram. Q0 is the start state, okay, and Q1 is the intermediate state, and Q2 being the final state. So this is a start state. Over a function 0, the transition happens from Q0 to Q0 itself, and Q0 over 1, it goes to Q1 state, and Q1 over 0, it goes to Q2 state. So this is one example. Okay, so yeah, let us moving further. Here 0 and 1 are the alphabets. Okay, so over these symbols, what is the transition happening is what is depicted in transition diagram. So from this transition diagram, if we write a table, it is called as transition table. Okay, so transition table comprises of the symbols here, which are the inputs, and on this side we have the states. So a combination of symbols and states is what we can say as transition table. Now transition function. So we have seen that in transition diagram, there is transition happening from one state to another state. So writing this in terms of equation, we come up with transition function. So we can depict as uh, we can depict as row. Okay, row of here current state would be written and here current input would be written is equal to either it remains in the same state or it goes to the next state or whichever state. This is how transition function is represented. Moving on further. So yeah, we are done with all the important concepts. Now we have something called as structural representation of finite automata. So let's see what structural representation of finite automata is. It can be represented by in terms of grammar, or it could be represented as regular expressions. So grammars and regular expressions, will be studying this in the upcoming videos, upcoming modules. But for your general understanding, grammar is a set of rules that are used to generate the sentences of a language. Okay, it is represented by G. Okay, next we have regular expressions. Regular expressions are the concised way of writing the transition diagrams. Okay, so if you write an equation to derive or a expression to derive this particular transition diagram, it is called as regular expressions. So this is what is about the structural representation of finite automata. So here we reach to an end of this particular video. If you have any doubts, do let me know in the comments and subscribe to my channel. Thank you. Stay tuned. I'll be uploading all the important topics module wise. And if you have any doubts, do let me know in the comments. Thank you.